This chapter 16 talks about acid and base equilibrium. By the end of this model, you will be able to define and identify Arrhenius acids and bases. Also, you will describe the nature of the hydrated proton represented as either H positive or H3O positive. You will identify and define Brønsted-Lowry's acids and bases and identify conjugated acid-base pairs. You will correlate the strength of an acid to the strength of its conjugated base. You will explain how the equilibrium position of a proton transfer reaction relates to the strength of the acids and bases involved. Also, you will describe the autoionization of water and explain how the concentration of H3O positive and the concentration of OH negative are related via Kw. You will calculate the pH of a solution given the concentration of H3O or the concentration of OH negative. You will calculate the pH of a strong acid or strong base given its concentration. You will calculate the Ka for a weak acid given its concentration and the pH of the solution, and vice versa. And finally, you will calculate the pH of a weak acid or its percent ionization given its concentration and the Ka. So let's start by learning some definitions of acid and bases. First, let's talk about the definition of Arrhenius. An acid is a substance that when dissolved in water increases the concentration of hydrogen ions, H positive. A base is a substance that when dissolved in water increases the concentration of hydroxide ions, OH negative. Also, there are other definitions. For example, Brønsted-Lowry defined an acid as a proton donor, and the base is a proton acceptor. So, using this Brønsted-Lowry acid and base definition, let's explain a little bit how they came with these definitions. A Brønsted-Lowry acid must have at least one removable acidic proton to donate. So, an acid the species that could be an acid must have this acidic proton. And remember that we talked a little bit about that before, that this proton must be in a covalent polar bond. Okay, so that in that way, there could be a difference in those electronegative and make the hydrogen more available, that proton. On the other hand, the Brønsted-Lowry base must have at least one non-bonding pair of electrons to accept a proton at H positive. So here we have an example of HCl plus water producing chlorine plus H3O positive. We can see here that this hydrogen is in a covalent polar bond because chlorine has a higher electronegative than the hydrogen, so that's why this is partial negative and this is partial positive. So with these two protons of oxygen, that could attract this hydrogen, and there you can form the H3O, and then the HCl, by removing that hydrogen, will produce the chlorine. So because of that, because this one give that proton, this is called the acid, and because this species receive the hydrogen, it's called the base. So in this reaction, the water acts as a base. Now, what happened with water? Water is really interesting because water can act as a Brønsted-Lowry base and accept a proton from an acid, as on the previous slide, but also can donate a proton and act as an acid, as in this reaction. Here we have NH3 and we have water. This will remove one hydrogen from water and create NH4, and when you release that hydrogen, you will have OH negative, because remember that you are removing one hydrogen. The hydrogen has a positive charge, and this one is neutral. So when you remove that positive, you may leave there a negative because you are broken that neutralization between those charges. The same aspect here. This one is neutral, doesn't have any charge, but when it received that proton with a positive charge, now turns to NH4 positive. So acid could act as a base, as we saw in the previous slides, or also could act as an acid. Because of that, the water is known to be amphiprotic. Okay, that means that it could be an acid. That species could be an acid or a base. It will depend with whom it's reacting. So let's see the term. Let's see the following slide about conjugated acid and bases. The term conjugated means joined together as a pair. Reactions between acid and bases always yield their conjugated bases and acids. So here we have HNO2 plus water producing NO2 negative plus H3O positive. So this um, anion comes from HNO2. So because to produce this one, HNO2 must release that hydrogen. So that's why HNO2 is an acid. And because this is an acid, this must be a base. And how can I confirm that? Because this will produce H3O. So the only way that this could produce H3O is by accepting a proton from HNO2. And because it's accepting a proton, this will be then a base. So now this is in equilibrium. Okay, so this means that it could go from left to right or also from right to left. Now, if we go, let's see if we go from right to left, we have here H3O positive, and this will produce H2O positive, H2O. So that means that this one release one hydrogen to produce water. So if this one releases hydrogen, this must be what? An acid. And this one must be a base because this one will produce this when it received the hydrogen from H2O. So this one must be the base. Now, interesting is that this one was produced by HNO2. So this is the acid and remove the hydrogen, and this is the conjugated base. So we have an acid that produced a base, and it's called a conjugated base. So this one is a base that produced a conjugated acid. Okay, so an acid will produce conjugated base, and the base will produce a conjugated acid. Some acids are better proton donors than others, and some bases are better proton acceptor than others. So here we have basically a list of different acids, and we can see here that the acid strength increased to the top, and in this list the base is a list of bases, and the base strength increased going down. Now, interesting, we can see that water is part of this list of an acid, of the acid list, and also here is part of the bases list. We know that water has the ability to be an acid or also a base because it's an amphiprotic molecule. So, when we're talking about the strength, acids above the line with water as a base, that means that we have here those acids and water as a base. So this is the line of water as a base. The acid over this line are strong acids, and their conjugated bases that are the ones that are here in the right. These are the acids, and this is the conjugated base. You can see here that this one is Cl. This doesn't have this proton, and also H2SO4 release one of the hydrogen, producing HSO4. These are the conjugated bases, and they do not act as base in water because this is really, really strong. Okay, so because this is really strong, these are weak. Now, also, bases below the line with water as an acid, here we have strong bases, and here we have water as an acid. So bases below this line as an acid, these bases are strong bases. And their conjugated acids, if these are basically the bases, these are the conjugated acids, do not act as acids in water. Okay, they do not act as acids in water. So we can see here that the more easily a base accepts a proton, the less easily its conjugated acid gives up a proton. In other words, the stronger an acid, the weaker its conjugated base. And the stronger a base, the weaker its conjugated acid. So the substance between also the lines with water are conjugated acid-base pairs in water. So these ones exist as an acid-base pair in water. This one you're gonna when this is in water, you're gonna see just the Cl, the conjugated base, because this dissociated completely. also the strong base. But in this case, where you have weak acid and weak bases, you're going to see both species in water. And as the same concept, this one is a strong base, a strong acid as compared to this one. So this one is a weak base as compared to this one. Okay, but you're going to find both of them because these are basically they are not that strong as the top, this top here, and also this bottom here. So you can find both of them, the acid and the conjugated base, or the base and the conjugated acid in water. So in every acid-base reaction, the equilibrium favors transfer of the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. Here we have HCl plus water producing H3O positive plus chlorine. So H2O is much stronger base than chlorine, so the equilibrium lies far to the right. Okay, this one is an acid and it's a strong acid, so that means that this is a weak base. Okay, so because this is a weak base, this one is stronger than this one. So here the equilibrium will shift to the right. Here we have acetic acid plus water producing H3O plus acetate. In this one, acetate is a stronger base than water, so the equilibrium favors to the left side. Okay, so when we have a stronger acid and a stronger base in the right side is gonna go to and the left side is gonna go to the right, and if it's in the products, it will shift to the left side. Let's talk now about the role of water. Water is amphoteric, as we mentioned before. In pure water, a few molecules act as bases and a few act as acids. So this is really important because you need both species to have an acid-base reaction. You can have just an acid doing its work if it's not a base. So you need both, okay, to create this reaction. So when you have just pure water, some of the molecules of water will act as bases, and the others will react as acid. And this is referred to as autoionization. So water, one molecule of water here and one here, one of them will release one hydrogen and the other one will accept it. So you're going to produce OH from one and you're going to produce H3O from the other one. Now, this basically here is an equilibrium, and here we see another expression for the same reaction. We have water here. This is a covalent bond, but it's also a polar bond because oxygen is more electronegative than hydrogen. So you can release this hydrogen or also this hydrogen, okay, by this unpaired electron. Or also you can remove this hydrogen or this hydrogen from this unpaired electrons. Okay, so in that way it could be either of them. So this one will remove the hydrogen from here, it will produce OH, and then you will produce from OH and from water and hydrogen the H3O. So the ion product constant. The equilibrium expression for this process is Kc equals to H3O, the concentration of H3O times the concentration of OH. Remember that I mentioned also in the lab that water, in this case, is a liquid, it's a pure liquid, so it's not part of the expression of the equilibrium constant, okay? So this special equilibrium constant is referred to as the ion product constant for water, that is Kw. So Kw is equal to the concentration of H3O times the concentration of OH, and the value for that Kw is 1.0 times 10 power of minus 14. Okay, so this also is equal to the concentration of H3O times the concentration of OH. So in aqueous solutions can be acidic, basic, or neutral. If a solution is neutral, that means that the concentration of H positive and OH, they are equal, okay, because they cancel each other, so you're going to have one species concentration larger than the other one. So a neutral solution will have both concentrations equal. Now, for an acidic solution, the concentration of the proton will be higher than the hydroxide ion. So the concentration of H positive will be higher than OH. This will be in an acidic solution. In a basic solution, the concentration of OH will be larger than the concentration of H3O. Now let's talk about pH. The pH is a method of reporting hydrogen ion concentration. pH is equal to minus log the concentration of H3O or H positive. Remember that H3O or H positive is the same as the concentration of protons. And the neutral pH is 7. Acidic pH is below 7. So if you have a pH below 7, you have a solution that has an acidic pH. If it's above 7, then that solution is a basic solution. So here we have a table basically with different concentrations and the pH and the pOH. So if pH is equal to the minus log of H positive, the pOH is equal to minus log of the concentration of OH, okay? And as you can see here, if the pH is 5, the pOH is going to be 9, okay? So the pH plus the pOH is going to be equal to 14. Now also, if you multiply this times this, okay, this one times 10 power of minus 4 multiplied by 1 plus 10 power of minus 10, this is going to be equal to 1 times 10 power of minus 14. Also, if you multiply this concentration of H positive is 1 times 10 minus 9 multiplied by 1 times 10 minus 5. This is concentration of OH. This one is going to be also equal to minus 14. Or if you have a pH of 10, the pOH for that solution is 4. Okay, so remember that you can express a pH of a solution, but also you can determine the pOH for that solution. For a neutral solution, the pH is going to be 7 and the pOH is going to be 7. For an acidic solution, for example, as 1, the pH is 1, but the pOH for that same solution is 13. Okay? So other P scales, the P in pH tells us to take the minus log of a quantity. In this case, the hydrogen ions. So some other P systems are the pOH, as I mentioned before, that is minus log of the concentration of hydroxide anions, and the pKw, that is the minus log of Kw. Remember that Kw is equal to the concentration of H3O positive times the concentration of OH. So the minus log Kw is equal to pKw. Now I mentioned a little bit, talk a little bit about this, the relation between pH and pOH. Sorry about that. So because the concentration of H3O positive times OH is equal to Kw, that this is equal to 1 times 10 minus 14, we can take the log of the equation. Okay, we can put minus log of this plus the minus log of this is going to be equal to the minus log of Kw, and the minus log of this is equal to 14. So now the minus log of H3O is pH, and this minus log of OH is pOH, and this minus log of Kw is pKw. So pH plus pOH is equal to 14. So if we have the pH of a solution, we can calculate the pOH by subtracting 14 minus the pH. So if we have a pH of 6, that means that the pOH for that same solution is 8. How do we measure the pH? We have several ways to measure the pH of a solution. Indicators, including litmus papers, are used for less accurate measurements. An indicator is one color in its acidic form and another color in its basic form. So as we can see here, this one is the methyl red, When the pH is 2, 4, and 6, lower than 7, remember that 7 is neutral, so these are acidics. So when you have this type of indicator and it's red, that means that that solution is acidic. If the solution is, when you use the methyl red is yellow, that means that your solution is a basic solution. Also, if this one is bromothymol blue, the same concept. If we add this indicator to a solution, it turns yellow. That solution is an acidic because here for yellow you have a pH of 2, 4, and 5. It's lower than 7. But if it's turned blue, that means that your solution is a basic solution because it turns blue when you have pH higher than 7. Also, we can use pH meters. That this one are for more accurate measurements of pH. We have electrodes that indicate small changes in voltage to detect the pH. So you can took this electrode and put it in a solution, and it will read the pH of that solution. In this case is 10.52. Now let's talk about strong acids. You will recall that the 7 strong acids are HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. These are by definition strong electrolytes and exist totally as ions in aqueous solution. So when you add this to water, what you're going to have in that vial is going to be H3O positive and the anion of the acid. So you're not going to have HA in that solution. You're going to have just H3O positive plus the anion of that acid. So for the monoprotic strong acids, we have that the concentration of H3O will be equal to the concentration of the acid. Okay, for monoprotic strong acid, the concentration of H3O is going to be equal to the concentration of acid. So if we have a concentration of HCl that is 2 molars, that means that the concentration of acid is 2 molar of H3O. Strong bases. Strong bases are the soluble hydroxides, which are the alkali metals and heavier alkaline earth metal hydroxides. So we can have calcium, Sr, barium. Again, this substance dissociated completely in aqueous solution. So when we have strong bases, that means that this M means metal, as alkali metal, and alkaline earth metal also, with OH. If in aqueous solution, this will dissociate it completely 100%, and you will have just the cation of this metal plus the OH. Or also, this one has 2 hydroxides, so it's basically the same concept. We have a strong base here is going to be completely dissociated, so we'll reproduce the metal with a charge of +2 and 2 OH. So for strong bases, it will be completely dissociated. Now, what will happen with the weak acids? For a weak acid, the equation for its dissociation is HA plus H2O in equilibrium with H3O positive plus A negative. What that means, that in a vial, if we add this acid with this water, we're going to have HA, we're going to have water, we're going to have H3O positive, and we're going to have also the conjugated base of this acid. So we're going to have the all 4 species in that vial. It's not completely dissociated as strong acids. Since it's in equilibrium, there is an equilibrium constant related to it, and it's called the acid-dissociation constant, the Ka. So the Ka is going to be equal to the concentration of the products divided by the reactant. Here, once again, we have water as pure liquid, so this is not part of the equation of this constant. So it will be the concentration of H3O times the concentration of OH divided by the concentration of the weak acid. Here we have some examples of different weak acids and their acid dissociation constants over here. The greater the value of Ka, the stronger is the acid. Okay, you're going to have a group of weak acid, and between those acids in that group, you're going to have stronger acid and you're going to have weaker acids, but all of them are weak acids. Okay, So comparing strong and weak acids. What is present in solution for a strong acid versus a weak acid? As I mentioned before, strong acids completely dissociated to ions. So you're going to have just the products um, in that beaker or whatever you have the reaction, or whatever you add the acid in the water. Okay. Weak acid only partially dissociated to ions. So that means that in that beaker, you're going to have the four species. You're going to have the two reactants and the two products if you have two and two. Okay. So here we have, for example, this is a strong acid, Ha plus H2O producing A minus plus H3O. And we can see here that all molecules, basically, these are the conjugated base, all of them. And you have also the H3O, that is the product when the water acts as a base and receive that proton from Ha. So in the strong acid, this is what you're going to see in that sample. And in the weak acid, as we can see here, the acid is Ha. In this case, is also a weak acid. So you're going to have some Ha molecules and a few H3O. Okay, so the difference is that you're going to have all four species here, also a molecule of water somewhere there. And here you're going to have just the products. Okay, when you have a strong acid, it's completely dissociated. When you have a weak acid, is partially dissociated. So let's calculate the acid dissociation constant from the pH. Let's do the following example. The pH of a 0.1 molar solution of formic acid, HCOOH, at 25 degrees is 2.38. So the pH is 2.38. Calculate the Ka for formic acid at this temperature. So basically the reaction, the acid-base reaction is formic acid plus water producing H3O proton plus HCOO negative. This is the reaction that we have. So we need to calculate Ka. Ka, remember that is equal to the concentration of products over the reactants. And in this case, water is not part of this equation because it's a pure liquid. So this concentration is part of the constant. So that's why the acid dissociation constant is the concentration of H3O times the concentration of HCOO divided by the formic acid. Now remember that we have formic acid and we add that to the water. So in the beginning of the reaction, we just have this and this. But when we mix them, it starts to produce H3O and HCOO. Now, how can we calculate the H3O positive? Where in which formula we have seen this expression of this concentration? In the pH, okay? So we need to look for the pH in this solution, and we know the value for the pH is 2.38. Okay, so by using this value of 2.38, we can do the anti-log, okay, anti-log of 2.38, and this will give us the concentration of H3O positive. But remember, the same amount that we produce from this one is the amount that we produce from this other product, because the coefficient of this one is 1 to 1. So if we produce 10 moles of this, we're going to produce also 10 moles of this. So that's why these concentrations are equal. So if we calculate the H3O positive, we have the concentration of HCOO. So here we have both concentration at equilibrium for this one and for this one. So we need to calculate the concentration of the formic acid in equilibrium. So to do that, let's go and create our famous Rice table. Okay, so we know that the initial concentration of the formic acid was this one, and the ion concentration was 0 molar in the beginning. So for the products, we don't have nothing. Now in equilibrium, we found that we have this concentration for both, for H3O and also for HCOO negative. So let's look for the table. Is this one, initial change equilibrium. We have here the formic acid concentration, the H3O concentration, and the HCOO concentration. At the beginning, we have 0.1 molar of HCOOH, and we have 0 molar of H3O and zero concentration of HCOO. But we know that at equilibrium we have the concentration of H3O and HCOO. Remember that we calculate this by using what? The pH. Okay, the antilog of the pH is 4.2 times power of minus 3. And because we have, this is the product, and this also is the product, and the coefficients are 1 to 1, so at equilibrium both concentrations are equal. So that means that the change of H3O from 0 to this was what? Positive. This, but remember that these are products, so as time goes by, you're going to increase the concentration of the product. So that's why it's positive 4.2 times 10 power of minus 3. The same will happen with the HCOO, negative. Now, what about the formic acid? What was the coefficient of the reaction? It was 1 to 1 to 1. So that means that this change is also the change for the formic acid, but this is reactant. So that means that it's going to be this value, but in negative. Okay? So now at equilibrium, we must subtract this value minus this one, and it's going to be 0.0958. That is basically 0.010. So as can you see here, this basically doesn't change because it's a weak base, or a weak acid, sorry, it's a weak acid. So the weak acid, they are not strong acids, so they not dissociate a lot. Okay, so basically they dissociate really small. So now we have the concentration at equilibrium for formic acid, for H3O, for HCOO. So now we can calculate the acid dissociation constant. So let's substitute the values in the equation of the acid dissociation constant, Ka. And by doing this, we can find that the Ka for the formic acid is 1.8 times 10 to minus power of minus 4. So let's calculate now the percent of ionization for a weak base. This is pretty simple. The equation is the concentration of H3O at equilibrium divided by the initial concentration of the weak acid. This multiplied by 100. So in this example, we have that the concentration of H3O was 4.2 times 10 powers minus 3, and the initial concentration was 0.10 molar. So we divide 4.2 times 10 powers 3 divided by 0.1, and all this multiplied by 100, and we have that the percent of ionization for this solution is 4.2%. So this is one pretty straightforward. The concentration of H3O divided by the at equilibrium divided by the concentration of the weak acid in the initial concentration of it. So let's now calculate the pH by using the Ka. We're going to have a few hints. We're going to mention a few hints now how to do that. So first, write the chemical equation for the ionization equilibrium. Then write the equilibrium constant expression. Number 3, the Rice table for the initial change in equilibrium concentration to determine the equilibrium concentration as a function of change. And then substitute the equilibrium concentrations into the equilibrium constant expression and solve for x and make assumptions if we can. Also remember in previous model that we can assume that the value of x is really small, and we avoid to use the quadratic expression. So let's do an example. Calculate the pH of a 0.3 molar solution of acetic acid HC2H3O2 at 25 degrees Celsius. So here we have the equation, okay, of the acid-base reaction. This one is acetic acid, so that's water will react as a base. So this will donate a hydrogen to the water, so the product will be the acetate right here, and also the proton H3O that was received by H2O. So These are the products, these are the reactant. So the expression of the acid dissociation constant will be the concentration of H3O times the concentration of the acetate divided by the concentration of the acetic acid. Once again, we don't put the expression of the concentration of water because it's a pure liquid and basically is constant. And then we create our table here. The initial concentration for acetic acid was 0.3 molar. For H3O and acetate was 0 and 0. That was the initial. Now the change, we don't know the change. So when we don't know the change, we must use a variable that in this case is going to be most of the time x. So the change for the reactants, the acetic acid, is minus x because you are going to consume this value. And for the water, H3O and acetate is going to be plus X. Both of them are products, so you're going to produce both of them. And at equilibrium, that means that we're going to have 0.3 minus X, and for H3O is going to be X, and for the acetate also is going to be the value of X. So the value of X is going to be H3O and the acetate. We're looking for the pH. So if we're looking for the pH, remember that pH is equal to the minus log of the concentration of H3O. Once we have the value of X, then we can calculate the pH because the value of X represent the concentration of H3O positive, but also represent the concentration of the acetate. Okay, but for us, we just look for the X and use it in the pH equation. So the Ka is going to be this expression as we mentioned before. We have x divided by 0.3 minus x. Here we basically assume that this x is really small, okay, to avoid to use the quadratic formula. So the expression is going to be s squared over 0.3 equals to Ka. Okay, that will be the expression right here. X squared divided by 0.3 is equal to Ka, that is this value. So let's now rearrange this equation. Let's move this 0.30 multiply by both sides. So we're going to have also x2 is equal to 1.8 times 0.3. Okay, this is multiplication. And there's going to be 5.4 times 10 to the minus 6. This is the value of x squared. So now we can apply the square root for this one and for this one. So we're going to have the value of x. X is going to be 2.3 times 10 power of minus 3. And as we mentioned before, the value of x is going to be equal to the value of the H3O. Okay, we basically define that variable as the concentration of H3O as well as the concentration of acetate, but we're looking for the concentration of H3O. So now we can look for the equation of the pH minus log of H3O and substitute this value, okay, of x right here. And this is going to be equal to 2. We apply the minus log, and the pH is going to be equal to 2.64. And this is expected because we are talking about acetic acid, so we expect a pH lower than 7, and it's 2.64. So let's talk a little bit more about strong versus weak acid. There is a few more characteristics that distinguish between the strong and the weak acid. Strong acid is going to be at equilibrium. We're going to have the concentration of H positive is going to be equal to the concentration of the strong acid that we had at the beginning because it's completely dissociated. Okay, so that's why they are equal. The weak acid, because the initial concentration is going to be larger than the concentration of H3O at equilibrium, and we saw that in the last example when we have the initial concentration was 0.1 and the concentration of H3O was 4.2 times of minus 4 or something like that. Well, but the thing is that was really small, the concentration at equilibrium of the H3O as compared to the concentration of the weak acid, the initial concentration of the weak acid. So this creates a difference in conductivity and in rates of chemical reactions. So here we're going to have a sample of chemical reaction. We have a piece here of metal, and we have both are acid. This is strong and this is weak acid. And as time goes by, we can see here they start to react. It's producing like hydrogen here. But this one basically is completely dissolve, okay, just react basically all the metal with the acid. And we can see that the reaction is complete with the strong acid, while with the weak acid is still reacting, doing the reaction. And eventually, also the weak acid is going to complete that reaction, but it took more time than the strong acid. So there's another really different, because with strong acid it's going to react faster than with weak acid. And to finish this model, we're going to talk about the polyprotic acids. Polyprotic acid have more than one acidic proton. So poly comes from two or more, and protic from proton. So we have more than one acidic proton in that compound. It is always easier to remove the first proton than any successive proton. So we're going to have, well, for the first is going to be more easy than the next hydrogen of the polyprotic acid. And is the factor, if the factor in the Ka values for the first and second dissociation has a difference of 3 or greater, the pH generally depends only on the first dissociation. Okay, so if we have a compound that has two acidic protons, and the difference in Ka between them is 3 or greater, okay, that means that the pH is going to be dictated by the first dissociation. And here we have a table, okay, with different acid. These are polyprotic acid. For example, here, phosphoric acid, H3PO4. It has 3 acid dissociation constant because we have 3 acidic protons here. And the first one, the Ka is 7.5 times power of minus 10 power of minus 3. This was minus 8, and this one is minus 13. So the difference between this one and this one is greater than 3. So the pH for a phosphoric solution is going to be dictated by the first acid dissociation constant.